So today we have a question which says that hot air at a temperature of 65 degrees Celsius is flowing through a steel pipe. So this is our pipe, right? A steel pipe of 120 millimeter diameter. So they didn't tell us whether the pipe diameter was the inside or the outside. But then anytime they give you the diameter of a pipe, specifically that's the internal diameter. But we don't use outside diameter to specify pipes, right? So this is 120 millimeters. The pipe is covered with two layers, and then there's a hot fluid, right? The pipe is covered with two layers of different insulating materials of thickness 60 millimeters. So this is the first layer. Let me call it one, 60 millimeters. And then the second one is layer two, 40 millimeters. And their corresponding thermal conductivities. So K1 is 0.24, K2 is 0.4. The inside and outside heat transfer coefficient are 60. So now the inside is as a result of the hot fluid here, right? So HHF 60 watts per meter degree Celsius. And then the outside. So now the atmosphere is at 20 degrees Celsius. So it means that the outside is as a result of the atmosphere, which is at a temperature of 20 degrees Celsius. The hot air was at a temperature of 65. Right? So HCF. I'm calling the atmosphere as the cold fluid, right? So that is 12 watts per meter degree Celsius. And then THF, temperature of the hot fluid, 65. Temperature of the cold fluid, 20 degrees Celsius. We are we are supposed to find the rate of heat loss from 60-meter length of pipe. Now the length has been given as 60 meters. Now we can find the rate of heat loss from the pipe using either the temperature change or the heat transfer from the hot fluid to the atmosphere, or from this point to this point, from this point to this point, any point, provided we have the temperatures at those two extremes we want to find. Now we don't have the temperature here and the temperature here, so we just have one option, to use the temperature from this portion to this portion. So our Q will now be 2 pi L multiplying. Now we are evaluating from this portion to this portion. So the temperature of the hot fluid minus temperature of the cold fluid, all over summation of all the resistances from that portion to the end. Now you are supposed to find the radii, right? And one thing you should also take note is that we weren't given the thermal conductivity of the steel pipe. So it means that the steel pipe is very thin, such that the thermal conductivity is negligible, right? So this portion is negligible. And that is why they didn't even specify the diameter, whether it was inside or outside. Exactly. So now we have the hot fluid flowing to the pipe, and then from the pipe to the first insulation layer, and then from the first insulation layer to the second insulation layer. So that's what we are doing here. Our Q now becomes 2 pi L. Our L is 60 multiplied by our THF is 65, and then our TCF is 20. So the summation of all the resistances from the hot fluid to the pipe is by convection, right? So 1 over HHF times R1, because that will be our radii, sorry, our radius, plus now from this point to this point is by conduction, right? So we'll learn R2 over R1 all over K1, plus from this point to this point is also by conduction. So we'll learn R3 over R2 all over K2. Now let's find our radii. We know R1 already, right? That is the diameter of the pipe. And then you're supposed to find the radius. So 120 over 2, and that gives us 60 millimeters. And in meters, it's 60 times 10 to the power minus 3 meters. And then R2. So R2 will be from, if this is the center of the pipe, from this portion to this portion. We know from here to here to be 60, right? So now when you add here, it's also 60. That becomes 60 plus 60, which is 120 millimeters. And then R3 is from here to here. If you know from here to here to be 120, you just need to add the 40, right? That's 40 thickness. So R3 is 120, which is R2, plus the 40, and that is 160 millimeters. So the rest is change of subject. Our K is equal to 2 times 3.142 times 60 multiplying 65 minus 20 all over 1 over, sorry, so this one, it loses from this point, it goes to the atmosphere, right? So plus 1 over HCF multiplied by R3, right? Because it uses the outside radius. So our HHF is 60 multiplied by our R1, supposed to be in meters. So 60 times 10 exponent minus 3 plus ln R2 over R1. Because it's a ratio, so you don't even have to convert into meters. So 120 divided by R1, which is 60, all over the K1, which is 0.24, plus ln R3, which is 160, divided by R2, 120, all over K2, which is 0.4, plus from the outer insulation to the atmosphere, which is 1 over the age of the cold fluid was 12 times R3. So you have to convert it into meters. So 123, which is 0.16 meters. So times 0.16 meters. So now we get our Q to be. Let's evaluate the numerator separately. 2 times 3.142 multiplying 60 times 65 minus 20. And that gives us 16966.8 all over. So with the denominator, we have 1 over 60 times 10 to the power minus 3 plus ln 120 divided by 60 all over 0.24 plus ln 160 divided by 120 all over 0.4 plus 1 over 12 times 0.16, and that gives us 4.406. So our Q now becomes 16966.8 all over 4.406, and then we have 3850.84 watts. So that becomes the rate of heat loss from the 60 meter pipe.